you very much, Max. So good afternoon. Oh, not yet. Good morning, everybody. So I would like to make an overview and some results from our network called AMOS. Most of you are familiar. I'm used to have these kind of the talks, kind of the review talks. And what is then more or less new, I will point to talks of my PhD students or colleagues, which were already done or which will be you will hear tomorrow. So it's a bunch of the collaborators, including our students. So I'm happy for this team. We are running the hardware, software, and some science behind it. So let me start with the motivation. Why we started this kind of the optical system we developed in 2006, 2007, the first prototype. Because at that time, a few years earlier, Neuschwanstein meteorite fell down, and it was very curious with the very similar orbit with the Příbram meteorite 43 years before, and it was puzzling whether there is any connection or it's just a chance occurrence because the type of the meteorites, Neuschwanstein and the Příbram was different. So there were kind of the hypotheses, okay, maybe it's some not homogeneous parent body, maybe some rubber pile from previous collision with different type of the material was the original body, disrupted and produced this kind of the possible, not meteoroid stream, but meteorite stream. So we started with the opposing to Pavol Spurný with some kind of the discussion we had, but later we came down, okay, let's try it, whether it's possible, whether we can find some mechanism which can produce this kind of the meteorite stream. So it was not a completely new idea to leave the rubber pile asteroid tidally break up in the Earth gravity field. So, but we tried to model it. We used the Itokawa asteroid as a example with the size frequency of the boulders and the particles which were observed from the Hayabusa 1 spacecraft at that time, and we did this kind of the model. What was surprising that these streams are not very numerous in the sense of the compared with the cometary streams, so there are not so many particles. And you need to collect data if there will be such a stream for many years. You will have maybe 1 or 2 meteors observed within the year. So you need to collect the data many years. You need to have the very wide field of cameras. So none of these very rare meteors will be out of field of view. You would like to have the very sensitive instruments to have the small sizes meteors, the small sizes meteorites, and it means that so we were thinking in this way, and we put the all-sky system, which is intensified. It's in a video regime, and this way the AMOS system originated. So that was the motivation behind. And maybe one more note. During this work, we discovered that there should be about roughly 10 these kind of the meteoroid streams originated from the tidally disrupted rubber pile asteroids. Well, within the time, they will be decoherent with the sporadic background. But we didn't see in the database any of such streams. So still, they might be very, very faint, not so numerous, but still real existing these kind of the streams in the Earth vicinity. But there is something for the community to still work on, not only to collect the data, but then search to have a good method to somehow discover it among the sporadic background. Okay, so let's introduce the AMOS itself. It's a, as I mentioned, it's an automatic observatory which we used in different places. Here it's in Mauna Kea Observatory. It has some outer cover to protect it with the weather, bad weather, or also during the daytime, because there is a image intensifier, very sensitive one, in the optical path of this system. And it has all sky part and also a spectral part. So the spectral part were developed later, but we call it AMOS spec. And here's the example of the composed images during the Geminids, I think from over Canary Islands, and one of the meteors with zero order with the emission spectra from the spectral part of the AMOS. It's very good for the orbital and spectral observation. It creates kind of the complex information we would like to gather. But time to time we also have some re-entries observations and some transient luminous events like sprites, and such unusual events also recording by the system automatically. It's placed, we started first in Slovakia, but then we extended to Canary Islands, Chile, Hawaii, Australia, South Africa, and recently one spectral system, it's in Arizona. And it's 7 locations, 17 all-sky cameras, and 18, and from the Monday, 19 spectral ones. So as I mentioned, it's not only the hardware, it's a software and trained students who try to do master and PhD thesis. So if you know about somebody, some students who would like to make or do the meteor science PhD studies in Bratislava, so let them know that they can contact me or my colleagues. Okay, so here is the dashboard system. We can monitor the health and information about the detections of AMOS stations. So it was developed by MartinBalaz, who is sitting here in this room, and it's quite clever system. It's a system on site on the computer at each side, and also it's a server on the upper side in Bratislava. So this is just an example of the AMOS with the nice volcanoes in Atacama Desert, how it looks like when it's open, but it's not during the daylight, it's just a service. We took this kind of the picture. And the statistics, just an example from Halakala Observatory at 3,000 meters altitude. So it was particularly in the year 2020. So about 30,000 detections, including some of the false detections. Here is some thunderstorms, but they're negligible to the total number of the meteors detected. So in general, we don't have too much false detections except the meteors. And you can see the night statistics with the nice clear showers activities. And one of the recent installation, it's Nalabor Desert, where previously Pavol Spurny had analog cameras in the past, and we are using the sites of the DFN network and the hands-on installation experience of these guys. You might know them. And now I just to try to make some overview example what kind of the detection we can have from one of our AMOS spectral system we used during the plane flight over Arizona in 2022 to cover the Tau Hercules display. So we also recorded the cluster. The cluster talk we heard from Pavol Koten, and Pavol and David Čapek analyzed this kind of the nice cluster with the 51 members. There are some subgroup of this recording because we have another recording from Jeremy Vebalion from his camera from the same plane. And other example of detection of the new meteor shower arids from the South Hemisphere. This is still not published yet. It's already a few years ago, so we maybe need to speed up the co-authors to finalize the paper. But we got several nice orbital solutions from this shower. It was quite weak, not too much, not too many meteors were bright. Even we have one spectrum with the very pronounced sodium line there. An example of the complex studies, including the fireballs. Here are two fireballs observed from Mauna Kea and Halakala, and spectral recording from the same time. This was the case also with some meteorite dropping, small meteorites dropping in the ocean, but we are usually not searching in the ocean. So there are some hardware scientists who do that. But we have complex information about the orbit and some characteristic about the atmospheric trajectory, some physical parameters we can extract, and also spectral information for the modeling of the composition. So, and recent activity of the ETA Virginits, Tomas Veres already mentioned some results of his modeling. Here are some orbital parameters, also very useful maybe for the meteor data center, but hopefully we will publish and revise the data soon. And you can see the radiant point. There are some nice exceptions. So the radiant, it's trailed because it was during the maybe two weeks activity of the ETA Virginits. And we can also observe one hyperbolic solution and one southern branch ETA Virginit. So that's also somehow depicted on the orbit, but there is also a branch of the complex other Virginit, kind of the sporadic background or broader background, which are close but distinguishable with the narrow ETA Virginit stream. Okay. And another example of the nice fireballs with the light curve, which has some strange behavior, some deeps, and Maria Paprskarova is playing with these kind of the things, try to model them. Maria, you will have okay, you will have tomorrow the presentation. Okay, so some details can be mentioned there, and we observed a very nice special case, calcium-rich meteorite according to the spectral information, on such a, let's say, regular orbit, near Apollo-type orbit. You can see some parameters here, with the possible connection to the specific meteor shower. They are close to each other, but we don't take too much care about the connectivity. But what is interesting, Filip Hlobik did some orbital evolution. It seems quite stable in this orbital space within the 500 years. But what is special, and this is also some stability plots. So Filip already had some talk about the orbital evolution of the kappa cygnets. So we see some properties which are close to the iron. I'm sorry, which are close to stony material. Depends on the different kind of the modeling. Maria prepared this slide for single body model. You can see that in general you can model somehow, but in details you couldn't. So in a gross fragmentation or in a differential ablation model, and maybe better if we'll put all these kind of the models together. So that will be a talk of Maria tomorrow. So we can find some differences. And it seems that there is two types of the material, and that is why Maria comes with the idea of the avocado model, that you have some maybe a lower density part, which has a very high ablation coefficient. It's not necessary to be such a muddy things like avocado is, but it might be very fragile part of the body, and then some core which has higher density and a lower ablation coefficient. And with this way, you can start to reproduce some features on the light curve. So that's probably more in detail you will be here tomorrow from Maria. And something we also heard from Tomas yesterday about the erosion model used for this special case, calcium-rich meteorite. We come with the original initial mass like 360 grams, and the bulk density, which is quite consistent with the stony material, a little bit higher mineralogical density, so there is might be some porosity. And finally, I can stop a little bit on the spectral characterization. So the upper spectra is this calcium-rich event, calcium-rich fireball, and it's rich really lines of calcium and titanium and other elements are quite unusual compared to the chondrite elements, but magnesium and iron, sodium, it's quite similar to chondrites. And from our laboratory test in a plasma wind tunnel in Stuttgart from recent years, we tested more than 25 different type of the meteorites, and we observed their emission spectra in the wind tunnel laboratory conditions, and we concluded this kind of the spectra is comparable with the Howardar or eucrite type of the meteorite. So it's not finally conclude, but they are really unusual compared to the chondrite composition we observed many times, but this is a really unusual one. And another case, it's from the Australia part of our network. It's a different spectrum, also to chondritic, strong in magnesium. It's the most strongest line in this comparison. And with the low iron lines in sensitivities, and it's very close to Albright from the last Hlobik case. So it's probably also this kind of the material close to Albright meteorite. So Adriana will also tomorrow talk about this laboratory test and other analysis which is ongoing. So that's another advertisement. So I already mentioned several of my students or former students. Thank you. And I'm close to conclude that the many of the authors, co-authors of the previous paper, but also some future plans are ongoing. So stay tuned, and we will have some results also published soon from the Meteorites conference recently in Perth. Okay, thank you for your attention. If you have any question.
Thank you, Juraj. Anyone has any question on the matter? Yep.
Have you reached the conclusion about the pairing of Pribram and Neuschwanstein?
So behind you, Chris, there is Pavol and Lukáš Hrbený, and they have some paper about kind of the conclusion. They also observed this kind of the stream regularly, maybe 10 years or 15 years, I don't remember exactly. You found some candidates which were probably close, but statistically not so significant. Maybe Pavol can specify.
Yes, you are right. We search for faint meteors on the similar orbits with Pribram and Neuschwanstein and found some candidates, but from the statistical point of view, it was not significant, and our conclusion was that this is a random coincidence.
But we still believe that might be somewhere in the noise, in the statistic, like a sporadic background. But now we are trying to analyze with one other student our recordings from the recent 15 years. So we will see whether we will find something similar or something new in the data.
Hi, Juraj. I wonder if your meteor cluster, in what time span did you receive those 51 or so meteors of the cluster as cluster members, and how do you qualify them? It's a discussion that goes back to the presentation of Pavol.
Yeah, as I remember correctly, it was within the 8 or 9 seconds, these 51 members. And you mean qualify whether they're connected to the same cluster, to the same region, or? Yeah, at that time, the Tau Hercules activity was declined. It was significantly declined when we observed through the window of the plane. We didn't see too much of them, and other cameras did not record it. But apparently, there were this kind of the cluster or the bunch of the meteors, and also Pavol did some radiant positioning, which correspond to the Tau Hercules. Yeah.
Thank you.
Okay. Oh, okay. Just one last question.
Maybe not a question, but a comment, but you reminded me with your comment in the second or first slide that you have some predictions, but you couldn't find it in your data later on, that there are potentially some other showers coming or on similar orbits.
Yeah.
So we internally in MDC, it's obnoxious plug again of MDC, but the thing is that we're actually discussing to collect information from dynamics, because up to 8 showers a body can create. But the thing is that sometimes you find them in your data, but the others do not. But maybe with time, with another team, or maybe the good time is happening, and then you might pick them up. It's just that to collect all of those solutions in MDC as well, like a separate list, and then we can always go back and see maybe somebody was looking for something in this area, and now we are seeing. So it's not to not encourage you to still do some statistical and dynamic work around those parent bodies, but it's just that it's already some of the work done. It just doesn't have a one centralized this kind of list that can be always look at and check it. So you kind of reminded me that we are looking in this direction as well, and maybe at some point some of those
Definitely, I will
orbits will be
contact
there.
you all the time.
Okay, thanks. So no question, just a comment and a plug.
Okay. Thanks again.